I should put this over here. There we go. Okay. Hi, everybody. Today we are going to be talking about section 4.3 in our statics textbook, and the subject of that is equilibrium in 3 dimensions. If you notice, I've posted the lecture for equilibrium in 2 dimensions, and today we'll have the lecture for 3 dimensions. It looks as though we have not covered section 4.2, but in reality, section 4.2 is a subset of 4.1, and the techniques for solving, there are some simplified techniques, but everything that you need to do for section 4.2 has been developed by talking about section 4.1. So having said that, the rest of it is that we'll have 2 lectures over equilibrium in 3D, number 16 and 17, and then lecture 18 will be the review for the midterm exam. That will be, then we have an entire week to schedule for the midterm. Now, when we do the review, I'll give you some problems that are exemplary of what's going to be on the midterm, and I'll discuss the process. I want you to rest assured you won't have to memorize anything. You'll be able to bring in a study sheet, so that's a good thing. But you have to make sure that your calculator is not, can't hook up to the internet, or if it is, you have to have a clear sign that it's not hooked up to the internet. But aside from that, we're good to go. No cell phones, of course, and I will keep my cell phone with me in case there's an emergency during the class. So you can keep your cell phone with you, but you just can't have it out. You can't use it in any way during the test. So you'll have lots of time next week to schedule for when you would like to take the test, being as it's a 2-hour block. But I will send out a poll no later than this weekend so that we can arrange for those times. All right. Having said that, does anybody have any questions about the homework to this point? Anything I can work for you? Or all right. Well, you guys are easy to get along with. So having said that, we'll just move right into section 4.3 when we talk about equilibrium in 3 dimensions. Okay. Now, with equilibrium in 2 dimensions, I'm going to talk about this for just 1 second. Said if all the stuff is going on in the XY plane, we have a rigid body, we have some forces acting on it. We know that the summation of forces X, summation of forces Y, and in this case all the moments about any point are going to be in the Z direction, and that in order for equilibrium to occur, those 3 conditions have to be met. All right, now if we're in 3 dimensions instead of 2 dimensions, in other words, if we have Y, X, and Z, where Z is, this is stylized, showing it coming out of the board, we're going to have 3 vector force equations that have to be equal to 0. And because then our moment is not defined as perpendicular to any particular plane, we're also going to have to do a summation of moments in all 3 vector directions equal to 0. So in 2 dimensions, we have 3 equations that we have to solve in order to establish equilibrium. In 3 dimensions, we have 6 equations that we have to solve in order to establish equilibrium. All right? Now, the other thing, of course, is when you're in 3 dimensions, we really can't rely on visualization skills. We have to rely on the math in order to complete this work. And I don't feel like anyone in the class resists that, but I have had classes in the past where certain people are very good at visualizing in 2 dimensions, and so they really rely on that skill. And I've been teaching this course for many years, and I've never seen anyone who can do it in 3 dimensions. So if you can, I'm open to that. But I'm just thinking it's not going to happen. So if you can do it, more power to you. So you'll be inventing the next great things in the next in the next 10 or 15 years. All right, so there are a lot of applications to this, but one thing I want to point out before we start working a problem is we also have a sheet, just like we did in section 4.1, about what the forces and moments look like on different types of supports and connectors. So if you have a support or connector and you're not really sure what kind of forces it will bear and what kind of moments it will bear, you can refer back to this sheet, and then you'll be able to work the problem with that information as well. The final thing before we go in, three-dimensional problems in general are very lengthy and very time-consuming. So I will only assign, I'll do one problem here to get us sort of squared away, and then I will give you probably one problem tonight and one problem Wednesday, because you should probably count on a while. And I apologize also, I know I work the problems very quickly when we're recording, but I also know that you can stop it and go back and look. So in no way am I implying that that should be your speed. I'm just doing it so that I don't have hours and hours and hours of a vodcast. So, so please forgive me in advance. All right, when I take a look at the end of the section problems, I kind of love a pole or a transmission tower problem, because these are very classical three-dimensional statics problems. So I will work 106 in class, and then I will definitely assign 108 for you as homework tonight. Okay, so in class, I'm going to work 4.106, and homework will be 4.108. Now, of course, I will put that on the homework assignment on the submit button, but you're only going to have one problem tonight, and then you'll have a different problem on Wednesday night, and then that's going to be it for us before the midterm. All right, so if we look at problem 4.106, we have a pole that we're told is 6 meters tall, and on this drawing, the y-axis is straight up, and the x-axis and the z-axis, neither one of them is drawn flush to horizontal or vertical. So we have x and z. Okay, we have a 6-foot pole. Let's see. I'd love to get some other color just to separate this out. I'll do some red here. So the pole is 6 feet tall. Okay, and the problem says it is acted upon by a 455 Newton force as shown. Okay, so there's a guy wire that's pulling from the top of the cable down to point F. It says the pole is to be held with a ball and socket joint here at A, right? And 2 cables, B to D and B to E. So B to D looks like this. This is point B. And B to E looks like this. Okay? For A is equal to 3 meters. In other words, where this connects at point F is 3 meters this way. Determine the tension in each cable. So we want to know the tension in BE, the tension in BD, and we also want to determine the reactions at A. So if we go back, well, I guess I could tell you, if you go back to that page in your book, what you'll find is that a ball and socket will bear a reaction in each of the directions. So in other words, the reaction at A, written as a vector, is going to just be a force, but it's going to be the reaction at A in the x direction plus the reaction at A in the y direction plus the reaction at A in the z direction. Okay? And now we know that the tension in BE can be expressed as, the vector can be expressed as the magnitude of the tension in BE times lambda, or the unit vector, along BE. And we know that the tension in BD can be expressed as the magnitude of the tension BD times lambda along BD. All right, so the first thing we need to do is to take our drawing and find the vector B to E and the vector B to D, and then reduce each of those to a unit vector. So since their drawing is quite a bit better than mine, let's think about B to E. B to E is pulling on the pole. B to D is pulling on the pole. Everything's pulling on the pole. Cables don't push very well. So when we start talking about BE, let's write the vector BE. B goes from B to E. So in the x direction, that is a positive 1.5. In the y direction, it's minus 3. And in the z direction, in other words, back into the board or out of the board, B to E is positive, comes out of the board by 3 meters in the k direction. So in order to find that lambda, the next thing I do is to find the length of BE. To do that, I use the Pythagorean theorem, three-dimensional version. And remember, when you square a number, it's always positive. So even though this is negative, I can just put it in as a positive because negative 3 is 9, just like it's positive 3 squared. So if I take 9, the radicand is 20.5. So I take the square root of 20.5, and I find that the length of that is 4.5 meters. Okay. What that means is I can write lambda BE as 1.5 over 4.5 I minus 3 over 4.5 J plus 3 over 4.5 K. All right, and you can probably see that out of 4.5, if you take 3 and divide it by 4.5, this value is 2/3, and this value is 1/3. So we can simplify that a little bit. I'm going to cross that off and do a little bit down here by saying lambda BE then is equal to 1/3 I minus 2/3 J plus 2/3 K. All right. So we'll be using this when we get into problem solving. Then we need to do the same. We've got lambda BE. We need to do the same for lambda BD. So the first thing we do is we find the vector BD, and we use our dimensions just like we did before. Okay, so this time from B to D, in the x direction, we come forward or to the right 1.5 meters, so it's positive 1.5. We come down 3 meters in the j direction, but now in the z direction, we're going back into the board 3 meters, so that's minus 3k. Right? So if you look at lambda BE, it's going to have the same, if you look at the length of BE, it's comprised of 1.5, 3, and 3. Even though the signs are different, this is also 1.5, 3, and 3, so we know that the length of this is also 4.5 meters. And so we can write lambda BD as 1.5 over 4.5, which we know to be 1/3 I, minus 2/3 J, minus 2/3 K. All right. Now, we still need to do this tension. The tension as a vector is going to be a little bit easier because we're given the magnitude of the tension, which is 455 newtons. But now we still need to write that unit vector, this time from C to F. So that's going to be lambda from this point. Why am I? Oh, that is C, because this, I'm sorry, these two come out here. This is actually way up here. Okay, so I apologize for that. This tension is 6 meters from A. These two tensions are only 3 meters from A. So these are correct, but my tension for that was drawn not to scale, to be sure. So now let's have our lambda from not from C to some point, or from B to some point, but from C to the point where it intersects the ground, which is F. All right, so from C to F, the vector CF, in the x direction, we go from here to here, and we are told in this problem that, we're doing 106, A is 3 meters, so from B to F, we are going back to the left, which is -3 meters in the I direction. In the J direction, we're going down 6 meters. On both of the other two, we were only going down 3 meters, but this is 6 meters. And then in the Z direction, we're coming out of the board, which is positive, or out of the plane of the paper, 2 meters. Okay. So that means my length of CF is the square root of 3 squared plus 6 squared plus 2 squared, which is the square root of 49, isn't it? Because this is 4 and 36 is 40 plus that is not 49. So that's equal to 7 meters. All right, so now my lambda CF then is going to be -3 over 7I minus 6 over 7J plus 2 over 7K. But the good news is we have this tension, so we can write the vector of that tension, which I'll call CF, is going to be -3/7 times 455 newtons I minus 6/7 times 455 newtons J plus 2/7 times 455 newtons K. So the tension in CF is -3 times 455 divided by 7, which is 195. And this is 6, so it's just twice that number, which is 390 minus 390J. And then we have 2/7, so it's going to be that number divided by 3. I'm just doing a little math shortcut there. So plus 130K, and that's in newtons. All right. Now we have all of the forces. We have 3 tensions, and we have the reaction at A. So the next thing we need to do is to write our equations for summation. Oh, that's a bad pen. Summation forces X equals 0, summation forces Y equals 0, and summation forces Z equals 0. All right, in the X direction, the reaction at A has a component in each of these. So we can start, and I've just called them positive just for the sake of simplicity. So our first term in each could be the component of that reaction in each of the directions. Now to that, I need to take into account my x, y, and z components of the tension. So I get minus 195 from TCF in the x direction, minus 390 from TCF in the j direction, and positive 130 from TCF in the k direction. All right, now I have these two other vectors. I have the tension in BE, so I need to write the tension in BE in the x direction, which is the magnitude of the tension of BE times the unit vector. And similarly here in the y direction, it's going to be like that, and in the j direction.
So we write all these tension things like tension of the cable, is that just to help us keep track of what number goes where?
Exactly.
So they're just, you don't necessarily need them in there, they're just helping keep track of.
That is exactly, well, we need to solve for that value. And so because each one of those equations is a force equation, you have to have it as a placeholder for that force because we're eventually going to have to solve for it. That is an excellent question. We're almost done. This is TBE. Now we need to do the same thing for TBD. And this is our last force. So TBD is also TBD, she says. Here it is also times 1/3 in the x direction. In this direction, it's a negative TBD times negative 2/3. And here it is a negative, I should put plus just to be consistent, 2/3. Okay. So what I want to show you to begin with is we have 1, 2, 3 equations, and we have 1, 2, 3, 4, 5 unknowns. Is there any way that we can solve that? If we have 5 unknowns, algebraically, we have to have 5 equations. So guess what we get to do? More equations. What would they be? How about the summation of moments in all vector directions about any given point equals 0? All right, now we're not going to have to go through everything that we did here because of, we're going to just take a breath and look at this for just a moment. If we take our moments about point A, all of the moments from point A go away, don't they? All right, so that's the good news. That means that we just have these 3 that are going to be creating moments. And further, we know the values of this. All right, so we can set up a determinant based on, I'm going to go ahead and set up 3 determinants here. So I'm going to say, let's take the moments about point A, because that will eliminate the reaction at A from the moment equations. Because if the moment arm is 0, there's no moment of the force. All right. So that means that if you look at these two, they're both from A to some point of action. If we just use R as being from A to B, which is purely y, and the distance is 3 meters, that's going to be 0I plus 3J plus 0K. And that's the moment arm that we can use for BE and BD. Okay, because B goes through the line of action of both of those forces. And then similarly, R from A to C, which is just 6 meters up, so it's 0I plus 6J plus 0K, I can use that for the 455 Newton force. Okay, so what I would do next is I would set up a determinant. I would say the moment about point A due to the tension, I'm going to do this one first because it's a little bit easier, in CF. When I do that determinant, remember the first row is IJK. The second row is my moment arm. And my third row are the components of the force. And here are the components of TCF. So this is minus 195, minus 390, and 130. All right, now I'm going to then do the same thing for the moments about A from, I want to work with this a little bit just to show you how to look for ways to simplify your work. But from TBE and TBD, okay? And when I set up that determinant, if I add those evaluated determinants together, they have to be equal to 0 in all three coordinate directions. So I know here that my top row is going to be IJK, my middle row is going to be 0, 3, 0, and then these will be the sums of TBE and TBD in the X, Y, and X, Y, and Z direction. But what I want to show you is, if you look at this, this is very similar, isn't it? When I evaluate this determinant, if I use this as my multiplier row, I'm going to get a lot less work because I have 2 zeros in it, okay? So you remember when I use a multiplier row, I start at position 1, 1, and I come down, so this has the same sign, different sign, this would have the same sign. 0 times anything is 0, so that doesn't matter. So all I get really out of this whole thing is just 6 times IK minus 195 and 130. Okay? Well, what that means for me here is that if I use the same multiplier row, that all I'm going to have is 3 times this IK. And then right here, I need to know this value, and I need to know this value. This is going to be TBEX plus TBDX. And this is going to be TBDBEZ plus TBDZ. Okay, so that just simplifies my work. Not a lot, but quite a bit more than I had before. All right. So, continuing with that, if I look at my components of tension in the X direction, I have 1/3 TBE plus 1/3 TBD. So I can factor out the 1/3, and I can just call this 1/3 times TBE plus TBD. And over here in the Z direction, I can factor out a 2/3, but this time it's going to be minus. So 2/3 times TBE minus TBD. So this kind of puts your arithmetic skills to the test. We got a lot of stuff. All right. So that means then in this position I have 1/3 times TBE plus TBD. And over here, I should have drawn this bigger. I have 2/3 times TBE. I'll redraw this in just a minute, minus TBD. All right. So as you may recall, let's see if I can find this quickly. When you have a little determinant like that, I don't know where it's written down, but it's just this number times this minus this times this. Okay? So MA about the moment about A caused by the tension in TCF is just 6 times 130I minus a negative, which is plus 195K. Okay, all right. And then the moment about A of TBE plus TBD is 3 times this, which is, I'm going to put another bracket here, 2/3 times TBE minus TBD. Then, so that's this times this, minus this times this, minus, oh, this is, I'm sorry, I didn't get my I in there. There's my I. Minus 1/3 times TBE, this time plus TBD times K. All right, so I've reduced those, I've got the products that are going to help me evaluate the determinants, and the math is going to get a lot easier because we're going to have a lot less substitution at this point. One thing that you'll notice on this equation is 3 times 2/3 is just 2, and 3 times 1/3 is just 1. So this actually, when I distribute the 3 through, that's going to simplify a little bit. So I get that that moment is equal to 2 times the quantity TBE minus TBD in the I direction, minus 1 times TBE plus TBD in the K direction. Okay, and this, I can multiply 6 through that and just get numbers. So I get 6 times 130 for my I, which is 780I, and then 195 times 6, which is 1170K. All right, so because of the way because of the fact that the pole is just purely J, we don't have any Y directional moments. We just have 2 moments. We have the X stuff that has to add to 0, and the Z stuff, which has to add to 0. So I pick out my X stuff. I have 780 from this part of the equation. And then I have plus 2, I'm going to go ahead and just distribute this through, 2 TBE minus 2 TBD. Those 3 things added together equal 0 in order for equilibrium to occur. And in the Z direction, I have 1170 plus, actually that would be minus, TBE minus TBD. Also equals 0. So after all that work, I have 2 equations and 2 unknowns. The easiest thing to do is to solve one of these equations for one of those variables and plug it back in. So I would start here. 1170 minus TBE is going to be equal to TBD. Then I can plug that in here, and I get 780 plus 2 times TBE minus 2 times 1170 minus TBE is equal to 0. So I'm almost home. We're on the home stretch here. So when I take 2 and multiply it by 1170, I get negative 2340 for this. And then I add to that 780. So the sum of my constants is 1,560, and my sign is negative. Then I have on the same side 2 TBE, and then negative times negative is plus 2 TBE, so that's equals 4 plus 4 TBE equals 0. I can bring the 1560 over to the other side of the equation, and it becomes positive. So TBE is 1560 divided by 4, which is 390 newtons. There's my first answer. I don't have to go back and reinvent the wheel. Now that I have TBE, I can plug it in right here. In other words, subtract it from 1170 and get a value for TBD, which is 780 newtons. Right? So I have TBE and TBD, and then it asks me for the reactions at A. Okay, I have 3 of them, so I can use those values. I'm going to write those values nicely at the top of a piece of paper so that I can use them effectively. TBD equals 780 newtons, and TBE equals 390 newtons. So now to get my reactions at A, I can go ahead and plug this in. I can say my reaction at A in the x direction minus 195 plus TBE times 1/3, 390 times 1/3 is 130, plus TBD times 1/3, 780 times 1/3 is 260. Those things added together have to equal 0 for equilibrium. So that means that my RAX is going to be, when I bring this over, that's positive, negative, negative. So I have 130 and 260 as negatives. 195 is a positive, so that's negative 195 newtons. In the y direction, we can do the same thing. We can say RAY minus 390 minus TBE times 2/3, which is 260 newtons, minus 2/3 times TBD, which is 780 times 2/3 is 520. Those added together equals 0. So once again, I can bring everything over on the other side, and they're all positives. So I take 520, add 260, add 390, and the value of RAY is 1170 newtons. And then last but not least, we're going to find R sub RA in the z direction. We know that we have 130. I want this right there, okay? And then TBE, which is 390, times 2/3 is 260. And then minus 780 times 2/3, which is 520. So I have plus, plus, minus equals 0. So that means that RAZ is, when this comes over, this is positive, this is negative, and this is negative. Okay? So that's 130 newtons. So that means I can write my reaction at A vector as my x component, minus 195I, my j component 1170J, plus 130K, and my units are newtons. So there's the vector that expresses my reaction at that ball and socket joint at A as a force. And then I also have the magnitude of the tension in both of the wires. All right. So you see why you're only going to get one homework problem. I mean, they're really something. This is like, to be honest with you, this is the absolute expression of everything we have done for half of a semester. This is everything. And I know it is just a real daunting thing to do, but you have all the steps. Now the key here is to pull everything together. And I don't mean to imply that's easy, but you do have all the pieces. So do you guys have any questions for me? No? All right. Well, I'll go ahead and stop recording at this point. Like I said, I'll post the one homework problem for you tonight.
And that's 4.108.
Yes, I think that's correct. I wrote it down at the top of something, and now I've slung papers so much I don't even know where that is. Yes, 4.108. So I'll post that homework problem for you under the submit button on the Podium PC right here. Then we'll have one more problem Wednesday, and that's it. Or Friday, excuse me, and that will be it before the midterm.
So are we getting one of those problems on midterm?
There will be an abbreviated one. What there will be is something that you can, and that's an awfully good question. There's two things I'd like to say about it. One is it won't be as difficult. If you set up the math, something will fall out a lot quicker than it did here. The other thing is that it's all about partial credit on those problems. So, so yeah, it's like, show me your work so that I can give you lots of partial credit. All right?
And you said you'll be doing the review in here on Monday?
Yes, that's correct. So, and I'll also record it. But it's great if you could be here because then you can ask me any questions. Or if there are any questions, if you're not able to be here Monday, if you email me any questions you have, I'll make sure to cover them on the review. All right? All right. Well, everybody, have a wonderful day, and we will see you for our last lecture on Chapter 4, Equilibrium in 3 Dimensions, in 2 days, and then we'll start talking about the midterm. You guys have a great day.